Today we'll be learning about thermodynamics. All right, so first of all, what is thermodynamics? Thermodynamics is the study of thermal energy and heat and their relationships to other forms of energy and energy transfer. And thermal energy is the energy associated with the motion of the atoms and molecules that make up an object. Therefore, the total kinetic energy of the moving atoms in the gas is how much thermal energy there is in an ideal gas. And in the diagram below, this right here is an ideal gas, which has high temperature and low pressure, and non-ideal gases have low temperature and high pressure. Okay, so these are the temperature scales. So temperature is also an ideal gas and is related to the average kinetic energy of atoms. Most thermometers work in different ways, and the ones at microscopic level depend on the speed of the object's atoms as they collide with the atoms in the thermometer. And this means that these thermometers are sampling the average kinetic energy of the atoms in the object. And these two equations in the bottom are how to convert from Fahrenheit to Celsius. So the first one is the temperature in Fahrenheit is equal to 9/5 times the temperature in Celsius plus 32. And the temperature in Celsius is equal to 5/9 times the temperature in Fahrenheit minus 32. But you have to subtract 32 first and then times 5/9 because the parentheses are in here compared to this one, which is just this part. Now, the temperature scales will also have a natural zero. So there will be a point at which kinetic energy is also zero. And we call this absolute zero. And no temperature below this is possible. And this is also defined as the Kelvin scale. And so from Celsius to Kelvin, it's K is equal to the degrees in Celsius plus 273. And from Kelvin to Celsius, it's C is equal to K minus 273. So you guys can do this first example. Okay, so it asked the coldest temperature ever measured was negative 190 90 degrees Fahrenheit in Antarctica. And what is this in Celsius and Kelvins? So using the equation 5/9 times TF minus 32, it's 5/9 times 29 minus 32. That equals negative 89 degrees Celsius. And then for Kelvins, it's just negative 89 plus 273, which is 184. So now we can move on to what is heat? So heat is energy transferred between two objects because of a temperature difference between them. So heat will also flow from the hotter object to the cooler one, and never from the cooler one to the hotter one. And we use Q as a symbol for heat. So you can see here that it goes from hot to cold, and then it eventually becomes equilibrium, like here. So it is obtained, thermal equilibrium is obtained when touching objects within a system reach the same temperature. Okay, so this is the first law of thermodynamics. So this is the most general statement for about energy and the conservation of energy. And the first law of thermodynamics is the formula above, which only the thermal energy changes. So if we just get rid of all these other stuff, then it would just be the change in the thermal energy is equal to the work plus the heat. So for systems in which only the thermal energy changes, the change in thermal energy is equal to the energy transferred into or out of the system as work, W, and heat, Q, or both. Okay, so now you guys can work on example 2. Okay, so in this question it says, if you mix food in a blender, the electric motor does work on the system, which consists of the food inside the container. This work can noticeably warm up the food. And suppose the blender motor runs at a power of 250 watts for 40 seconds. During this time, 2000 joules of heat flow from the warmer food to its cooler surroundings. By how much does the thermal energy of the food increase? So if you use the first law of thermodynamics, which is this one kind of fine. So the change in the thermal energy is equal to the work plus the heat. So since we're given the power and the time, we know that work is equal to the power times the change in time. So it'd be 250 watts and then times 40 seconds. So that would equal 10,000 joules for work. And then it says that 2,000 joules of heat flow from no warmer food with cooler surroundings. So since it's even, then it would be minus 2,000 for the Q. So it'd be the change would be equal to 10,000 and then minus 2,000 because it's leaving. So the change would be 8,000. Okay, so now I'll talk about reversible and irreversible processes. So a process is reversible if it doesn't violate any laws of physics and it goes backwards in time. For example, when an ice cube is placed on a table in a warm room, it will melt, and this is an irreversible process because the ice cube won't form out of a puddle of water. However, at a microscopic level, collisions between molecules are completely reversible. So in this case, for our gases and thermodynamics, a lot of stuff can be reversible. And this is the second law of thermodynamics and also entropy. So entropy is the measure of amount of disorder. So in this graph or in this picture, it starts off here like this, and then increase in entropy for this is for gases, by the way. So you see how they get more spread out, and that's an increase in entropy and an increase in disorder. So when disorder increases, entropy increases, and when disorder decreases, entropy decreases. And the second law states that the entropy of an isolated system never decreases. Therefore, on this first part, doesn't happen. So disorder can't decrease, it can only increase. And the entropy either increases until the system reaches equilibrium, or if the system began in equilibrium, it stays at equilibrium. Okay, so this is the definition of a mole. So one way to specify the amount of substance in a system is to give its mass. Another way, one connected to the number of atoms is to measure the amount of substances in moles. And 1 mole, abbreviated as 1 mol, is 6.02 times 10 to the power 23 basic particles. And Avogadro's number is equal to 6.02 times 10 to the power 23 moles per negative 1. So this is the equation right here. So this is the number of particles is equal to the number of moles times Avogadro's number. So it's generally written as n is equal to n divided by Na. And this is used to find the amount of moles. Okay, so this is the atomic model of an ideal gas. So the temperature of an ideal gas is a measure of the average kinetic energy of the atoms that make up the gas. So right here, it says this shows that the kinetic energy of atom or molecule in joules is equal to 3/2 times K, which is Boltzmann's constant right here, and T, which is the temperature of gas in kelvins. And it can also be written as 3/2 times N times Boltzmann's constant times T. And to find the temperature, it would be 2/3 times the kinetic average divided by Boltzmann's constant. Okay, so I'll go over pressure really quickly. So pressure is just P is equal to the force divided by the surface area, and it can also be written as force is equal to the pressure times the area. A gas exerts a force of magnitude on a surface of area A. Okay, so now these are the ideal gas laws. So This one is the most common version. So P is the pressure of the gas, and V is the volume of the gas. So you multiply those, and it's equal to the number of moles times R, which is the gas constant, and it's given right here. But this one is the one you should use, 8.3 times mole. And is equal to the number of moles, the gas constant times the temperature. And also shown right here. But it can also be equal to N times Boltzmann's constant times T. Okay, so you guys can do example 3. I forgot to tell you that right here it says it has a pressure of 1 atm, and 1 atm is equal to the pressure is 1 atm, which is equal to 101.3 times 10 to the 3 pascals. Okay, so you guys put from the problem down. Okay, so to do this question, it says what volume is occupied by 1 mole of an ideal gas at a pressure of 1 atm and a temperature of 0 C. So we would use the equation the pressure times V is equal to nRT. And since the pressure I said was 1 atm, which is 101.3 times 10 power 3 times the volume V is equal to N, which is just 1 times R, which I said um, on the other page was 8.31. So it'd be 8.31 times T. And since T should be in kelvins and we're given that the temperature is at 0 Celsius, so it'd be T is equal to the temperature at C plus 273. So 0 plus 273 is 273. So times 273. So to find B, it would be 1 times 8.31 times 273 divided by 101.3 times 10 power 3. And you would get 0.00224, I think, cubed. Oh, sorry, it's 0.0224. which is the same thing as 22.4 liters. Okay, so now I'll talk about the ideal gas processes. So using the equation from before, we're going to assume that, so we're going to move the T over to this side by dividing it, and we assume that's constant. And then we can write that final is equal, this final part is equal to the initial part. And the initial and final states for ideal gas in the same container are constant and equal. So first I'll talk about the constant volume process. So if you have a gas in a closed rigid container, forming the gas will raise its pressure without changing its volume. And this is an example of a constant volume process. So the volume, final volume and initial volume for a constant volume process. And it appears on a PV, which is a pressure and volume diagram, as a vertical line. So since the volume isn't changing, it would just be the pressure that's changing. And so it would be a straight line. So this is the initial and this would be the final. Okay, so now there's also a constant pressure process. And like the other one, many gas processes take place at a constant pressure. A constant pressure process is also called an isobaric process. Isobaric process. In this kind of process, the final pressure is equal to the initial pressure, and a constant pressure process appears on a PV diagram as a horizontal line. So in this case, the volume is changing, and in this isobaric process, the pressure is going from this initial to this final. And then we have a constant temperature process. So a constant temperature process is also called an isothermal process. And in this case, the final temperature is equal to the initial temperature. Because there's an inverse relationship between P and V, the graph of an isothermal process is a hyperbola. So it would be like this. Okay, so now we talk about our final topic, which is specific heat. And if heat C is required to raise the temperature of 1 kg of some substance by 1 K, then heat MC is needed to raise the temperature of mass M by 1 K as well. So MC, which is the mass, times the heat and times the change in temperature is equal to the heat. Oh, specific heat. So considering problem 1. Oh, and I'll give you like 2 minutes to do this one. Okay, so for this question, it says a researcher measures the kinetic energy of a chair sliding on a rough floor. At the beginning of the motion, um, at the beginning of motion, the chair has a kinetic energy of 35 joules, and once the chair stops sliding, the kinetic energy is zero. So what can you conclude by the researcher's results? So if you look at the possible answers, it talks about the two laws of thermodynamics that we learned, and you can already cancel the first and third one because this problem has nothing to do with entropy and the second law of thermodynamics. So either um, the results are invalid or valid because the first law of thermodynamics is not violated because energy is not destroyed, and that's true because um, the kinetic energy isn't getting destroyed; it's just transferring to something to a different kind of energy. So it would be two instead of four. Okay, so this is the answer. Okay, so this is problem two. Okay, so this question says, which of the following was result in a heat transfer? So it would be two, this one, because a temperature gradient, heat transfer is when heat transfers from hot to cold, and that's exactly what the temperature gradient is. So I'll let you guys read the solution here. Oh, sorry. Okay, so now you guys can work on problem three. Okay, so it says 1.4 kg, which is just 1,400 joules of energy, is applied to an aluminum rod of unknown mass. Its temperature goes from 20 Celsius to 45 degrees Celsius. What is the mass of the rod? And it's giving you the specific heat. So using the equation, the heat is equal to the mass times the specific heat times the changing temperature. We're trying to find the mass. So it would be mass is equal to the heat, which would give us over C times the change in temperature. It would be 1,400 joules divided by C, which is 0.9, and then times the change in temperature, which is, since it goes from 20 to 45 degrees, the change is just 45 minus 20, which is 25. And sorry, and if you saw that you had 22.22 grams. Okay, so this is a solution. Okay, so this is problem 4. Okay, so this question says you have 50 grams of water in a container above a burner. If 14 kJ, which is 14,000 energy, is put into the container, assuming all of it goes to the water, uh, the specific key of water is 4.17, how much did the water temperature rise? So using the equation again, it'd be start to T. And this time we're trying to find the changing temperature. It would be the changing temperature is equal to Q over MC. So Q is 14,000. M is 40 grams. 50 grams, and C is 4.17. That equals 67.15 degrees. Okay, so this is the solution. Okay, so this is question 5. Okay, yeah. So question says Anna is holding onto an ice cube, and why does it not in her hand? So yeah, it'd be the heat from her hand forms it, and because of the second law of thermodynamics. So this solution. Okay, so this is question 6. Okay, so it says a balloon is in a room that has a constant pressure of 100 kPa and a constant temperature of 20 degrees Celsius. How many moles of air must be put into the balloon for 20 joules of work to be done in the balloon? So um, work is equal to the pressure times the change in volume. I'm using the equation P times delta V is equal to nRT. You know that this part is same as work, so work is equal to the number of moles times R times T. And we're trying to find the moles of air. So N is equal to the work divided by R times T. So the work is given as 20 joules divided by R, which is 8.31. And then temperature, which is since you're giving it 20 degrees Celsius, the temperature for Kelvins is TC plus 273. So we 20 plus 273 is 293. Yeah, yeah. And this is the solution right here. So we use work as this and then put it into the equation to get 8.2 moles. Okay, so this is problem 7. Okay, so in this question it says, suppose that a gas originally at standard temperature and pressure undergoes a change in which its pressure is quadrupled and its temperature is cut in half. What change in volume did the gas experience through this process? So if the original volume is just V, then we would choose equation PV equals nRT. And if so this is the new V volume, this is the change volume. So if the pressure is quadruple, so 4V is equal to nR times T over 2. And we move everything to this side, so it's be V equals N RT over 2 divided by 4B. So it would be nRT E over 8. Oh, nRT over 8P. So in this original one, V is equal to nRT over P. So if we substitute that, it would be 1/8 times V. So it would be decreased by a factor of 8. And this is the solution here. Okay, so do you guys understand this one? All right, well, I'm just seeing one question. Okay, so for this question, it says at 40 degrees Celsius, the volume of a gas is 300 milliliters. So the temperature of the gas gets raised to 55 degrees Celsius with no change in pressure. So what is the new volume of the gas? So based on what we learned before, which is PV over T initial, is the initial. I don't remember it's again. So PV over T initial is equal to PV over T final. And since the B is constant, we get rid of that. So so V1 over T1 is equal to V2 over T2. So at 40 degrees Celsius, so so we're trying to find the new volume of the gas. So we're trying to find V2. So V2 is equal to V1 times T2 over T1. So we're given that's 300 milliliters. So V would just be 0.3 liters. And then that's times T2, which is 55 degrees Celsius. But we have to write the temperature in Kelvin, so be 55 plus 273. And then divided by T1, which is 40 degrees Celsius. But again, we have to write in Kelvin, so it'll be 40 plus 273. 273. And you would get 0.3 liters, which is 3 to 14. So here is the answer. Okay, so I'll just go until you guys do one more question. Wait, Yeah, you guys can do this question. I do this question. And I'll give you 2 minutes. Okay, so it says the pressure of a sample of gas is 5 atm in a 1.2 liter sealed flexible container. If the pressure gets raised to 8 atm at a constant temperature, so this part's important. What is the new volume? So using the equation from before, the initial and final. Since the temperature is constant, we need a way to get rid of that. So it's be the P1 V1 is equal to P2 V2. So since we're given that the first pressure is 5 atm, so it's 5 times 1.2 is good to the pressure of the second one, which is 8 times V2, which is the new volume. So to find V2, let's do 5 times 1.2 over 8. And we don't need to put the pressure into a different unit since they're both the same. So that would just give us 6/8, which is 0.75 liters. This is VB. Okay, so this is the station. Okay, so thank you for coming to today's class, and I hope you guys have a great weekend.